Hi, I'm Siao and I'm from Group 6. Today I will briefly present our work on case study 2 with the title of Production of Methanol in Chemtech M. Sdn Bhd as part of our process control and instrumentation course. This study focuses on understanding and modeling the dynamic behavior of a methanol distillation column. So during our industry training at CTRL Group Sdn Bhd, we were tasked with analyzing a pure methanol distillation column. The aim was to study its dynamic behavior through mathematical modeling, determine key parameters like steady-state gain and time constants, and simulate its response using MATLAB simulating. So to guide our analysis, we broke the problem into three parts: what we already know, what we need to know, and our learning issues. First, we already know includes the operation of a pure methanol distillation column, the use of first principle modeling, and the basic concept of chemical engineering. We were also familiar with parameters like flow rate, concentration, and assumptions typically used in process modeling, such as ideal trace and constant relative volatility. Second, what we needed to know was how to model the system dynamically. This includes determining the time constant, understanding first order and first order plus dead time models, and how different inputs like feed flow rate or composition affect the column's performance. We also needed to figure out how the column reacts to a step change in inputs. Lastly, our learning issues were more technical. We had to learn how to apply Laplace transform, linearize nonlinear equations, derive transfer function, and use MATLAB simulating to simulate system behavior. We also needed to understand tools like the initial and final value theorems, impulse and pulse functions, and how to interpret the simulation's result. Together, this framework helped us focus our effort and build a deeper understanding of dynamic process control. This is the provided document in Case Study 2A and Case Study 2B, where the figures show the methanol water continuous distillation column and the tables show the methanol water distillation input parameters. To simplify the modeling process, we make several assumptions. For example, we assume perfect mixing on trace, constant relative volatility, and negligible vapor power. This assumption helps us focus on the key dynamics without overcomplicating the system. In Part 2A, we derived dynamic models for each section of the column, including the feed tray, top and bottom trays, condenser, and reboiler. Each of these was modeled based on total mass, component, and energy balances. This provided a full dynamic representation of the distillation process. So this slide shows the working step for feed tray. And this is the working step for top tray, bottom tray, I tray where the I is 2, 3, 4, and n minus 1. Then this is for the condenser. And lastly is the reboiler. Next, in Part 2B, we apply Laplace transform to convert our time domain equations into S-domain transfer function. This allows us to create input-output models and analyze how changes in input like heat composition or flow rates affect the methanol concentration across the column. So this is the working step for feed tray with mass balance, then component balance. This is the input-output models for component balance of feed tray, and then for energy balance, and this is the input-output models equation for energy balance in feed tray. Then we also do for top tray with the mass balance, component balance, and energy balance. Then bottom tray, I tray with I equals 2, 3, 4, and until n minus 1. Then for condenser, and lastly for reboiler. After deriving the dynamic models for each section of the column, we move on to develop the transfer functions for selected trays, specifically the feed tray and the top tray. The transfer function represents the relationship between an input variable such as feed composition or flow rate and the output variables, which in our case is the methanol concentration at certain tray. From the transfer function, we could extract key dynamic parameters like steady-state gain and time constant, which tell us how fast the system responds and how sensitive it is to the changes in input. These transfer functions were essential for our later simulation and help us understand the dynamic response of the methanol column. And this is the first transfer function for in feed tray. And this is the second transfer function in fit rate. So in fit rate, there are two transfer functions. And in top tray, there is only one transfer function. We then use MATLAB Simulink to simulate the effect of a 5% step change in input variables. For example, we have studied how a small increase in feed composition or feed flow rate or reflux flow rate impacted the methanol purity. So from this simulation, we can observe how long the system takes to stabilize and how sensitive it is to each variable. And that's all for my presentation on the methanol distillation case study. Thank you for listening.